Hi, physics. This is Mr. Janowski with the next part of the chapter 4 slides. So the do now questions. How fast is 40 meters per second in miles per hour, approximately? So remember the bloody cheetah. So what you do if you ever get a speed in meters per second, just double that number, and that will get you close enough to that speed in miles per hour. So it's not a great approximation. It's not super accurate, but it gets you in the ballpark. It's close enough. And this is important because whenever you get a velocity, a speed or a velocity this year, quickly do this. Get it from meters per second into miles per hour, and then ask yourself, okay, well, now that I know the speed in miles per hour, is that a reasonable speed for this object, this baseball, this soccer ball, this car, this thing? So, yeah, remember the bloody cheetah. Question 2, what is the difference between speed and velocity? Speed is the scalar, velocity is the vector. So they're basically the same thing, only if you're talking about velocity, you care about the direction of the thing. So how does velocity relate to distance and time? It's actually the same formula as for speed, only again, we care about the direction. Velocity is distance over time, or V equals D over T. And what are the units for velocity? Throughout most of the year, the units for velocity we will use will be meters per second. And back to this idea from the motion maps. If you're watching the car, well, I'm sorry, you're not watching the car. The car has gone by, dripping oil at a constant rate, and you're looking at the pattern of dots that are left behind. In this situation, the location of the drops will give you the displacement. That's where the car was relative to where it started. The spacing between the drops gives you the velocity. So the further, the greater the distance between the drops, the faster the car was moving, the higher its velocity. And how the spacing between the drops changes gives you the acceleration. So the fact that the dots start small, or the distance between the dots starts small and then gets greater and greater, means that this car is accelerating. It's gaining velocity as it goes to the right. So its velocity is to the right, and its acceleration is also to the right. So, do objects fall at a constant rate? In fact, they do not. A common misconception, something that Aristotle would have thought, things just fall at a constant rate because it's in their nature to do so, according to Aristotle. But that's not actually true. So, the example I used in class was if I were to drop an apple to you from a height of 1 or 2 meters, you would just catch it. Wouldn't be a big deal. If I got up on top of the roof of the school and dropped the same apple to you, you would be afraid. This would be scary. The apple would be moving much faster if I dropped it off of the roof of the school. So this is demonstrating to us that objects gain speed as they fall from rest. So we can think about this in terms of mechanical equilibrium, an idea from chapters 2 and 3. So if I'm just holding the apple in my hand and it's not moving, it's experiencing two forces. It has its weight going down, which is the force due to gravity, and it has a normal force from my hand. So my hand and the apple are in contact. Therefore, my hand is exerting a normal force on the apple. In this case, if I'm just holding it there, the forces just exactly cancel. So the amount of weight going down is exactly equal to the normal force going up. So when I add the forces together, the sum of the forces, sigma f, equals 0. And that means the apple is in mechanical equilibrium. So the apple was at rest. There was no net force on it. So it just remains at rest. Now, if I suddenly release the apple, if I quickly remove my hand from here, the apple no longer feels the normal force. It only feels its weight, the force due to gravity, which means the sum of the forces is no longer 0. So it's no longer in mechanical equilibrium, and its motion has to change. So it will go from rest to it's experiencing a force down, so it's going to start moving down. It's going to accelerate downwards. And the entire time that it's falling down, there is no net force. I'm sorry, there is a net force on the apple, which means its motion won't be constant. It won't fall down with a constant speed. Because there is a net force on it, its motion will change. It will accelerate as it goes downwards. So objects in free fall accelerate downward at a constant rate. They don't move at a constant rate. That would be velocity. They accelerate at a constant rate. The rate at which their velocity is changing is constant, as long as we can ignore air resistance. So an object is in free fall if gravity is the only force acting on it. So no normal force from my hand, but also no air resistance. So we're going to say that we can just ignore that. That force will be small. We're just going to ignore it. And the weird result of this is that in physics class, we will say that an object is in free fall even if it's moving up. As long as gravity is the only force acting on it, we say that it is in free fall. So if I throw the apple up in the air and catch it again, even when the apple is on its way up, we're going to say that it is in free fall. So we use the idea of fall differently than people do in regular everyday conversation. So if you could ignore air resistance, do more massive objects accelerate faster than less massive ones? If you can ignore air resistance, they do not. Ignoring air resistance, all objects will accelerate downwards at the same rate. So we'll get to that in a second. There's some videos about that. Now, if we can't ignore air resistance, so if I'm in a room full of air and I drop a hammer and a feather from the same height and I let them go at the same time, the hammer will accelerate faster. The hammer will win the race from my hand to the ground. The hammer will get there faster because air resistance will affect both of these objects, but it will affect the feather much more because the feather has less mass. So a small amount of air resistance will have a big effect on the feather, but not a noticeable effect on the hammer compared to its weight. So back to this idea, do more massive objects fall faster? Do they accelerate faster? And the answer is no. So they do feel a greater force of gravity. So let's say that the hammer has 100 times the mass of the feather. So if you let them go, the hammer feels 100 times as much force due to gravity, its weight, than the feather does. However, because it's more massive, it also takes 100 times as much force to get it to accelerate as quickly as the feather. So these two factors, there's more weight, which is more force due to gravity, and also greater inertia, will just exactly cancel. So in the absence of air resistance, any object you drop is going to accelerate downwards at the same rate as any other object, which is the point of these two videos. So I'll put links to these videos in the description to my own video here. So one is the short one from Apollo 15, where an astronaut actually does drop a hammer and a feather from the same height on the surface of the moon, where there is very thin atmosphere, so you can't ignore air resistance, and they both fall down and accelerate downwards at the same rate. And then the longer video is of a vacuum chamber. So this is something that NASA has where they test equipment that's going to be out in the vacuum of space. So in this video, they lift up a bowling ball and a bunch of big feathers to a great height, several stories tall, and then they release them. The first time they release them, there is air in the room, and so exactly what you would expect happens. The bowling ball accelerates down much faster than the feathers. The feathers just kind of waft back and forth gently until they get down to the table in the ground below. The second time they do this, they have pumped all of the air out of the room, or very nearly all of the air out of the room. So it is in a vacuum, so there's no more air resistance. So if they drop them both at the same time, they both accelerate downwards at the same time. So again, I will put links to these videos in the description to my own video. And then the last thing we did in class was this Kahoot on units and symbols. So it will be very important, in this chapter, but also throughout the whole year, know what units and symbols we're dealing with. So yeah, you have to be fluent in these things to do well in physics. So I'll put a link to this in the description as well. So that's it for these slides. Hopefully you found that helpful.